only change B field. So let's say you have a wire here. We're looking at the cross-sectional area of the wire. So now let's say you have original B field out of the board. So let's say the original B field, B initial, is 2 milliteslas out of the board, right? Out of board. So now let's say the final magnetic field is 4 milliteslas out of board. And so let's say the radius of this wire is 20 centimeters. And then the resistance of the wire is equal to 10 ohms. And let's say the number of loops is 60 loops. So now we can ask questions such as, what is the electrical field induced in the wire? What is E field induced in the wire and its direction? B, what is the EMF in the wire? And then what is the current? What is the current and its direction? What is the magnetic field created by this current? Created by this current and its direction. So if you can kind of understand this, this is a prototypic type of problem, but we could of course vary this, but this is kind of like the base from which we can understand Faraday's law. So this is known as basically Faraday's law. Michael Faraday. Okay, so let's see here. So we're gonna say the B field is uniform across the area of the wire, right? So it's 2 milliteslas. So it's uniform. So then you just literally have this equation, E times 2 pi r, right? The dl. So that's going to be the E times 2 pi r, and then that's going to equal negative. So in our case, the area is constant. The angle between the area vector and see, the B vector is coming out of the board, and the area vector, we're going to make the default area vector out of the board. Remember, two-dimensional objects don't really have an area vector, a defined area vector, but we're going to make the default area out of the board because that's usually positive. So then the angle between the B and the A is just 0. So we just have negative A cosine 0, and then dB dt. The only thing that's changing in our case is the B field, right? Yeah, just dB dt, and the A and the cosine 0 come out. And then now we have here cosine 0 is 1, so negative, and then the area is pi r squared. And then the dB dt is B final minus B initial over delta t. In our case, we don't have to, it's not really a derivative because you're given the initial and the final. So B final minus B initial over T. And then the pi cancels, the pi cancels, the R cancels, the R cancels. And then we have here E is equal to negative R over 2. Okay. Times B final minus B initial over delta T. Okay, so now we have negative, we can put the radius of the wire, 0.2 over 2. And then B final is 4 millitesla, 4, and then minus the B initial is 2. Then I'll just put here milli on the outside. Oh, they also have to tell us how many seconds it took to go from here to here. So let's say 1 second. So in other words, the rate of change of the magnetic field, how long it's going from its initial value to its final value. So for B final minus B initial over the time interval. So if the T is 1 second, we just put 1 second. Okay, so then we're gonna have here, then the rest is we just calculate 4 minus 2 is 2, 2 and 2 cancel. So the electric field is negative 0.2 milli, and then that's volts per meter. That kind of looks weird, huh? Millivolts per meter. It looks like this is meter. So probably it's better to write negative 0.2 millinewton per coulomb. Because remember, volts per meter is the same thing as Newton per coulomb. Okay, so then what is the electrical field induced in the wire? So notice to calculate the electrical field, we don't use the number of loops. So we just use the regular Faraday's law, E dot dl, and we don't have the N, the number of loops. Then the negative means clockwise usually. Okay, clockwise. So in a second, I'll explain to you why negatives clockwise. So instead of writing negative, we're just gonna say, we're gonna give the absolute value, the magnitude of the electrical field, 0.2 millinewton per coulomb, and we're gonna say the direction of the electric field is clockwise. Okay, so what does that mean? So inside of this wire, by changing the B field from 2 to 4, you are creating an electric field inside of the wire that's pushing the protons this way. Of course, we know that it's not actually protons that flow, right? It's not positive charges that flow, it's negative charges that flow the other way. But it has the same effect. So remember, we do positive current flow. So in other words, the clockwise electric field will give rise to a clockwise current. That's the idea. A clockwise induced electric field will give rise to a clockwise current. So now we'll see in a couple seconds why we need to produce a clockwise current. So now question B says, what is the EMF in the wire? So to calculate the EMF, you do the number of loops times the electric field times the circumference of the circle. So the whatever electric field you calculated times 2 pi r times the number of loops. Because each turn of wire is increasing the voltage, right? In other words, you go once around, you come back, you're at a higher voltage. Then you go back around, then you're at a higher voltage, you know, so you keep the voltage. Actually, it's the opposite. Each time you go around, you add a lower voltage. Remember, positive charge flows from higher voltage to lower voltage. So you kind of go around, it's almost like a staircase. You're going around like this, like this, like this, like this, you see. So the first loop of wire, you're at the higher point. So the current is flowing this way. Then when it comes back, it's below where it started. You see that? It's like this. It's below. So you've lost voltage. Then you go like this, you've lost more voltage. Then you go like this, you lost more voltage. You see that? So that's why the number of loops decides how much voltage you've lost overall. The EMF is equal to NE 2 pi R. It's beautiful how this works. So 60 loops times 0.2 for the electrical field, but then it's a milli, 10 to the minus 3. And then 2 pi times the radius of the circle, which is 0.2. So this one was the electrical field, milli, number of turns. See, by adding more turns, I can create an EMF that's more and more noticeable. It's noticeable, definitely. 15.1 millivolts is the EMF that's induced. So again, I'm focusing here on the magnitude, 15.1 millivolts. Now the current is going to be 15.1 divided by the total resistance of the wire. So it's telling us that the total resistance of the wire, including all 60 loops, the total resistance is 10 ohms. So then the current is just going to be EMF over R. So divide this by 10, and then that's going to be 1.51 milliamps. Right? And which direction is the current going to be? What is the direction of the current? Same as the direction of the clockwise electric field. So you see it's going to go like this, down, down. It's like a parking lot. Parking lot. You see, each time you're going down, let's say you're on the highest floor, right? Then you go across, then you come, you're at the, let's say, ELAC parking lot, 7th floor roof, right? You go, then you go down, and you're now you're on the 6th floor. Then you're on the 5th floor. You keep going down, and the total voltage you've lost is the total loss in potential energy. You see, so then you have the current is 1.5, and then the direction is clockwise. Okay. So now, what is the B field created by this current? So remember from last chapter, we know that when you have current in a wire, it will create its own B field. You see, this B field that I had written was the external B field. So now I'm going to induce a current, you see. So in other words, here's what's happening in Faraday's law. By changing the external B field, you are inducing an electric field in a wire. That electric field is inducing the current, and then that current is creating its own B field. So what's going to be the direction of the B field created by that current? Well, if it's clockwise current, what's the direction of the B field? Curl your fingers in the direction of the current. It's into the board, right? So the current here is going to create a B field in this region that is into the board. Does that make sense? Why is it into the board? Well, that goes to Lenz's law, you see. So the Lenz's law is saying that when the magnetic flux is changing, the electric field created is in such a way as to be opposite of the direction. That's why the negative is placed. It happens to be opposite of the direction of the change of the B field, right? It's not necessarily opposite of the B field. It's the opposite of the dB/dt, not the B, right? So in other words, it's the opposite of the direction of the change of the B that caused it. And so therefore, the current that's induced in the wire is going to be in such a way as to fight against. So the B field was out of the board, 2 millitesla, and now I have increased it. So to fight against that, I am now gonna create a current that it creates a B field into the board to fight against this increase. You see? And so what's gonna be the magnitude of the B created by this current? Well, we're just gonna calculate the B created right at the center. Remember earlier in that chapter, we calculated that the B at the sides is gonna be larger, right, than the B in the center. But we're just gonna get the B in the center just to get a ballpark. So the B in the center is N mu 0 I over 2R. That's going to be the magnetic field created by that induced current, and it's going to be into the board. Into the board. Okay, so then you're gonna do the number of turns, 60. 4 pi times 10 to the minus 7. And then the current is this guy, 1.51 milliamps over 2 times the radius, which is 0.2. So it's going to be a weak field, but at least it will fight against the change of the B field that's producing it. Let's see, so we have here 60 times 4 pi, 4 times pi, times 1.51 divided by 0.4. 2846. Okay, but then I've got the milli, which is going to be divided by 1,000. Okay, then I could go back one more space and then write it as B is 0.285 microteslas into the board. So the B field created by the induced current is gonna be 0.285 microtesla. Right? And you might say, okay, that's not a big deal. So what would have happened? Why is it so important that the B field be into the board? Even if it had been out of the board, this B field wouldn't have been even noticeable, you see. So that was, so everything would have been the same. You would have created a current that was 1.5 milliamps counterclockwise. 1.51 milliamps counterclockwise. So then the current would have been like this. You see, and then that current would have created a field that was 0.285 microtesla. You see, so then you go like this out of the board, 0.285 microtesla out of board, versus 0.285 microtesla into board. But then 0.285 microtesla is so small out of board that when you add it to this, I mean, it's hardly noticeable. So what would have happened? In other words, why isn't nature operating this way? What bad thing would have happened out of this scenario that we're saying, oh no, there must be a negative there? Right? So in other words, why does 0.285 microtesla has to be into the board, the B field? Anyone know? You could answer too, Daniel, if you want.
Oh, because you can have extra B field coming out of the board instead of just the 4 milliteslas, right?
Excuse me?
Yeah, because you're saying, so why does it have to be into the board, right?
Yeah. So in other words, if this is hardly noticeable anyway, the current created by this scenario is very small, and the B field created by that current is very small anyway. So why is it that important that it be into the board instead of out of the board? It's hardly noticeable, so what's the big deal?
Well, because that would be more like you'd end up with like a positive feedback loop, right? Like you if you increase the current, you'd have more B field going in the same direction, and you'd get like how do I put this? Like
Okay. I think you're onto it. You're onto it. Yeah. Say that again. Okay. Go in your direction of thought of the positive feedback loop.
Right. Because like oh yeah, because I was gonna say like you have more if you have more current going counterclockwise, you'd start increasing the effect of the magnetic field going towards us. So I don't know how to put this. Like it would go out of control in a way.
Yeah. Okay. Look. Imagine that you have this scenario and you say, okay, yeah, it's not that noticeable. But then now if you redo the calculation and you say, okay, if you go through the calculation, cosine 0, and then you have B final minus B initial over delta T, right? So then you have E times 2 pi R is equal to A. So then what was my B final? 4 milliteslas, right? So 0.004 Tesla. But actually I have to add now to it the B field created by that induced current, right? So 0.000000. Yeah, it is hardly noticeable, but then you have this minus the initial B field, which is 0.002 over 1 second. But you see, even though it's hardly noticeable, now look what's going to happen. Because this makes this even larger, right? And now you subtract this. Now you create a slightly more current, slightly more than that, but not that noticeable. But then that current also creates a B field slightly larger than this, you see, also out of the board. You see how the feedback loop is going to happen? So now there's going to be an E field, plus there's going to be an EMF, plus there's going to be a current that's slightly bigger than this, 1.51000000, let's say 834 something. But then that current is going to create a B field slightly bigger than this, 850000348, let's say, out of the board. So then that goes back into here, you see, and gets added to this. This is all happening instantaneously, of course. So if this law of nature hadn't had a negative, what would have happened is all this would have happened instantaneously. We wouldn't even notice it. This would go feedback loop back into there, and it would create more current in the counterclockwise direction, and then keep going. And before you know it, the currents that you're creating are not milliamps, but they're actually amps. And the B field you're creating are not microteslas, but they're actually Teslas. So just by changing the B field once, by itself, you've created all this feedback loop, and you've created current out of nothing. You see, energy out of nothing. And the energy will keep going by itself. You don't even have to do anything. Do you see that? It's amazing. So why there has to be a negative there? You see, the negative will ensure that the current created is clockwise, which is going to tend to reduce the field that you do. right? And when it reduces it, it's going to keep creating a feedback loop to fight against you. So in order to keep creating current, you're going to have to keep changing the B field, you see? If you just change it once and leave it there, you see, it's not going to, this feedback loop is going to kill the current eventually, you see, because it's fighting against you. Instantaneously, it's like it's creating a bunch of feedback loops that's fighting against you, not helping you. So that's why you can't have a perpetual motion machine. You know, you can't just do something once and it help you. I guess that's kind of the idea of Lenz's law. But you hit it on the head. Good job. Lenz's law. Named after the physicist Emil Lenz, who formulated it in 1834. So that's probably around the time of Faraday, too, the early 1830s. The direction of the electric current, which is induced in the conductor by a changing magnetic field, is such that the magnetic field created by the induced current opposes the initial changing magnetic field. Notice it doesn't say it opposes the magnetic field, but it opposes the changing magnetic field. It is a qualitative law that specifies the direction of the induced current, but states nothing about its magnitude. So it's kind of focusing more on this negative. What does it mean to say negative right here? So if we go back to the original question and switch the order, let's say the B initial had been 4 milliteslas out of the board, and then the B final had been 2 milliteslas. How would that have changed the answer? I'm going to show you what I mean by the current and the B field created don't necessarily fight the B, but the change of the B. So far, maybe you don't know what I mean by that. So if the B initial is 4 out of the board, and B final is 2 milliteslas out of board. See, both of them are out of board. So then what's going to happen? E 2 pi r. So we could go through the same kind of calculation. A times cosine 0. So now you have here, there's a negative. So now you have B final minus B initial over delta t. You see? So now what's going to happen? The pi cancels. R cancels, negative R over 2. B final is 2 minus B initial is 4 over 1 second. Right? And then you're going to have here 2 minus 4 is negative 2 over 1 second. And now notice the two negatives are going to cancel, and 2, and you're going to get 0.2, right? Or there was also a milli here. So 0.2 for the radius, newtons per coulomb. So now it comes out positive, and positive usually means counterclockwise. So the electric field is counterclockwise. Okay, so now what's happening? Just to make it quick, we'll just say CCW for counterclockwise, and then CW for clockwise. So it's CCW in this case. So now the current that it creates will be the same as before, but counterclockwise. 1.51 milliamps counterclockwise. And the B field that it creates will be 0.285 microteslas in, let's see here, out of board, right? Out of board. So now notice that even though the two B fields, the original Bs are both out of the board, the current you're creating creates a B field out of the board. So it doesn't fight against the B field, but it fights against the change of the B, you see? The B is starting with 4, but it's getting weaker. It's getting weaker. And so therefore, it's afraid, the thing is afraid that the B field is gonna start dying out. So what it does is it creates a current that's this way, that itself creates a B field out of the board to help the original B, not to fight against it. You see? In the first case, the B field is getting larger and it says, oh no, I don't want it getting larger. So it helps, it fights against the B. Here it says, oh no, it's getting weaker. So it actually helps it, you see? So that's what I meant by Lenz's law saying the current direction is not necessarily against the B, but against the change of the B. If it's getting weaker, it tries to help it. If it's getting stronger, it fights it, you see?